This one is on contrast formation, and part of my assignment was to say something about the effect of CS correction, and another thing was to say something about use of Zernica type phase contrast. But first I will go through some basics of the assumption that some of the students would like to hear about some basic things. The most important element, in my opinion, in the electron microscope is the objective lens. And there are a lot of key things about the objective lens that are worth having a really good understanding about. The object, of course, the specimen, but the issue or the element about the object is not the object, but the electron wave that is transmitted through the object. And I will be referring to that as the exit wave, or the transmitted wave of the electron. Then another key thing I'll be mentioning is the three things about the objective lens. The focal length, which you often hear about or think about, the distance between the lens and the object, and the distance between the lens and the image. Two things very useful to know, that the objective lens produces an in-focus image at a distance di, when the object is at a distance do for object. That satisfies this kind of algebraic relation. 1 over the distance to the object plus 1 over the distance to the image are equal to 1 over the focal length. And that's called the lens law. And associated with it is the magnification is given by the ratio, distance to the object divided by distance to the image. And as we heard earlier today, in addition to the objective lens, then there's a series of subsequent lenses whose focal lengths can be adjusted so that the final viewing screen becomes conjugate either to this first image plane or to the focal plane. And of course, if the relay lenses are set to produce an image of the focal plane and you have a crystal, then you see an electron diffraction pattern. So I will often refer to the electron diffraction pattern that is produced in the back focal plane, even if it is not a set of diffraction spots. You know, it's really continuous scattering. I might still call it electron diffraction pattern. Now, already getting into something that may be a little bit controversial, the ideal goal of making a perfect optical system, a perfect microscope, the goal is to produce at the image plane a magnified version of the intensity of the transmitted wave in the exit plane. You want to make a magnified image of that intensity, and you would like to have exactly the same intensity distribution on your detector as there exists in the exit wave. And imperfect lenses never quite accomplish that. But the more perfect you make the lens, the more exactly the same intensity is here as the intensity of the transmitted wave. So perfect is defined as being the image is exactly in focus in the way I defined it earlier with the lens law. So the image is perfectly in focus, exactly in focus. There are no lens aberrations. And the resulting image, the resolution in the image is limited only by diffraction effects, meaning that the electrons, or it could be light, that's scattered at too high of an angle to be accepted by the lens, then that for spatial frequencies higher than associated with that scattering angle, they can't be in this image, so it won't be that's called a diffraction limited image. And so the highest quality light optics are pretty much diffraction limited. Electron optics, we're not normally so fortunate, but the recent development of aberration correctors bring electron optics very close to the same goal of being diffraction limited. So having a perfect lens works very well for objects in which the intensity in the exit plane varies with X and Y. As in the case of a light microscope where you have some stained cells, you have some PSC, something stained, and there's amplitude or intensity modulations, then you want to image those as exactly as you can. But it obviously does not work for transparent objects because if the object is transparent, there is constant intensity. And you bust your buns trying to get an image that gives you an exact magnified version of this constant intensity, and then you're disappointed when there's no contrast. Obviously doesn't work for transparent objects. And in his Nobel acceptance lecture, Zernicke explained all of this in a more formal way than I have just done. And he said, but that never bothered the microscopist. They just defocused the image a little bit so they could see the tricky details. And of course, that's what we do in the electron microscope. So, the optics of a defocused objective lens. There's a simple way to think about this and a complicated way. We heard the complicated way this morning. The simple way is to say that if we have a transparent object, a phase object, so there are no amplitude variations in the exit plane, in the exit wave, but there may be variations in the phase because electrons going through one part have experienced one refractive index and then going through another part have experienced some other refractive index. And so the phase is variant, but there's constant intensity. Well, if you go to a plane some distance delta z below that, there will be Fresnel diffraction effects because it's no longer a plane wave that's been transmitted. There are phase modulations. And those give rise to Fresnel diffraction. And the constructive and destructive interference in the Fresnel diffraction pattern, you all know what Fresnel means when you defocus a hole in a holy carbon film or something. See the Fresnel fringes. So those intensity variations now are imaged by this perfect lens as perfectly as possible to give an image that has contrast in it. That's the easy way to think about it. The more mathematical way is obvious diffraction theory, that in a more formal way, which says you take the exit wave, do its Fourier transform, multiply it by a wave aberration function that contains spherical aberration and defocus. That's more correct because the simple way I described it did not account for spherical aberration. So I don't know an easy way to explain spherical aberration. I have to fall back on an obvious formal theory of image formation. And the resulting image intensity with the magnification factor on the xy coordinates is the square of an image wave function that's convoluted with a point spread function. And Fourier transform that gives you the familiar CTF function, at which I'm not going to develop, which is already developed this moment. Now, first point. If we talk about the optics of a defocused objective lens, spherical aberration in electron microscopy is either our friend or it is irrelevant. It doesn't matter at all. So in some circumstances, spherical aberration is our friend. If you are at so-called Scherzer defocus, so these two simulations using a program that Henry made available to the community are at exactly the same defocus. So in both cases, defocus, the 300 keV electrons defocused by 70 nanometers, assuming an optimistic energy spread, and a reasonably good collimation of illumination, reasonably good spatial coherence. If you had no spherical aberration without a corrector, then the CTF oscillations would set in earlier at lower resolution than they do if you have spherical aberration. Well-known effect. If you are under focus, Spherical aberration and defocus tend to cancel each other out, giving you a broad zone of contrast transfer. Get rid of spherical aberration in the microscope, and you lose that advantage. So let's see, what else? Oh, I'm trying to figure out where I am on my slide. If somebody wants to ask a question, they're welcome to do so. There's a problem. Yeah, sure.
So in that case, that the CS corrected image will have the sort of what's called a lower resolution limit.
The so-called information limit, the spatial frequency at which you get the first zero. Yeah, would be worse with a CS corrected
microscope. Would this be a disadvantage for the material scientists or
I think the reason is that you just take the same defocus value.
Yes.
But you would certainly take a different defocus value in a CS corrected microscope.
But which defocus value should you take? I can't speak for the material scientists.
Yeah,
so the material scientists never have weak phase objects.
Yeah, they usually take a shared focus, right?
This is,
but with the CS corrected, it might be different.
A couple of nanometers. So you just are able to do something similar to Scherzer focus, but with an additional parameter of CS. So you can have 3 maxima instead of the 2 in the upper figure here with the CS corrected microscope. So just adjust the defocus in such a way to optimize your imaging conditions. So this is not optimal, but
so I'm sure the material scientists are smart enough to know what they should do about defocus when they have spherical aberration correction. I'm not, but I'm sure they are. I'm only concerned if we have weak phase objects. So something to point out that, so in this case, CS is our friend, but this is not a very good case for biologists to be doing electron microscopy because the low spatial frequency, so this is 16 angstrom resolution, 123 angstrom resolution, this is a log scale. So for things that are kind of low spatial frequencies, low resolution features that are so important in your ability to see a particle in the micrograph, there is almost no contrast. And this is the point that Zernicka made and the point I was making. The intensity is constant at those spatial frequencies. There's no contrast. So we have to defocus a lot more. And so instead of 70 nanometers, we have to defocus about 20 times more that. 10 or 20 times that much in order to see our particles. So typically a micrometer defocus. In order to make this function start coming up a lot earlier and get some contrast transfer at those spatial frequencies. And the downside, as you all very well know, is that when you defocus to get contrast, then this thing oscillates like mad. Okay. So let's consider that case, that we are now going to defocus by 1.4 micrometers and either have a CS of 2 millimeters or a corrected one. There's no difference. There has to be some difference, but I can't see the difference. All right, so it's irrelevant. CS correction, if you have to defocus enough to see your particle, CS correction is irrelevant. It's not going to do anything for you at all. It might cost you something in your grant. But if you submit a grant proposal saying you want a CS corrector and you're going to defocus this much, be sure to declare that I have a conflict of interest as a reviewer. You don't want me to be a reviewer on that grant.
So I think the envelope is even worse.
It's not any better.
No, the envelope is worse. I think that's the difference.
I don't think so. But you will look at it for sure on your software. I looked at it a bit and decided I can't see the difference. All right, so close enough for government work, as I said. CS has a negligible effect on the CTF when the defocus is this high or even higher. But you're not talking about CS anymore. What I want to take the opportunity to point out is that you can overcome this horrible envelope by making your beam more parallel. Essentially make the spot size smaller. And so if illumination angle alpha, you make it not 2 times 10 minus 4, but 2 times 7 minus 5, then the envelope is pretty good. Of course, the CC, the chromatic aberration envelope, or the temporal coherence envelope, doesn't care at all what the how parallel the illumination is, but the spatial coherence envelope is very, very sensitive. And this shows you how rapid these oscillations are and how well you have to estimate the defocus in order to correct the CTF when you are defocused by 1.4 micrometers. So all of that sets me up for this next slide, which says that Zernica phase contrast optics is a better way to produce image contrast for phase objects. You must apply a phase shift to the scattered wave if you have a phase object. Yeah.
Can I just ask, before we shift on to this, then,
Yeah.
is there any advantage to developing a CS corrected microscope?
Is there an advantage to developing a CS corrector?
Corrected microscope?
Corrected.
From what you're saying, it seems to be like there isn't any.
I don't know of any for phase objects, for weak phase objects.
Big phase object. Yeah, so the main advantage is in high resolution material science.
Material science,
That
but not
makes,
biology.
that makes a really a big difference.
You know, or if you combine it with this.
Or you could combine it with Zernica. But you need to have a specimen where there's a reasonable expectation that your resolution will be higher than 2.5 or 3 angstroms, or else there's no advantage. All right. I'm not trying to take a poll or anything, but are there a few people in the audience who have used a Zernica phase contrast light microscope? I do. Yeah, okay. So you're familiar with the principle and why it works? No. Maybe I will explain. So the principle of the Zernica phase contrast microscope, imagine this is a light microscope. You have light being transmitted. There's constant intensity because it's a transparent object, but there are phase modulations because the refractive index is not the same everywhere. And so the phase of this exit wave varies with x and y depending on what it is in its path. And even though the intensity of the exit wave is constant, the phase is not constant. In the case of electrons, the refractive index is a result of the Coulomb potential of the individual atoms. So every atom has a positively charged nucleus. It's surrounded, it's shielded by the electrons, but there still is enough residual effect that the projected Coulomb potential of neutral atoms causes phase modulations. You're looking down a helix versus looking across a loop, there's very different phase shift that is imposed on the electrons that are transmitted through the sample. And so in a Zernica phase contrast microscope, the phase modulations result in an electron diffraction pattern at the back focal plane. If this is a crystal, diffraction pattern is discrete spots. If it's not a crystal, it's continuous scattering, but in my mind, I think of it still as a diffraction pattern. And in this back focal plane, the unscattered electrons are focused to a point, and all of the scattered electrons are off to one side. So the wonderful property of the back focal plane is it physically separates the unscattered electrons from the scattered electrons. And once they're physically separated, you can put in a little slab of something that will cause a 90-degree phase shift for the scattered ones that have a hole. For the unscattered electrons, they don't get that 90-degree phase shift. And that's how the zertical light microscope works. Am I right, Anchi? You have to rotate in the condenser, you have to rotate in the annular device so that you can better separate the, in the back focal plane of the light microscope, the transmitted from the unscattered electrons. And the light and the scattered light gets 90-degree phase shift. So this selective phase shift here produces contrast in image intensity, just as does defocus. So defocus is nothing but a phase plate caused by the combination of defocus and spherical aberration. When we write down the obvious theory of image formation formally, we treat it that way. Mathematically, we say, we have a diffracted wave here, we now multiply it by e to the I of gamma. That's a phase shift. And the function of the 90-degree phase shift is to convert phase modulations to amplitude modulations. That's the function of the 90-degree phase shift. But if we do it with a phase plate, the phase shift is one value. It's, let's say, 90 degrees, pi over 2, everywhere, at all spatial frequencies. You know, not just at the band that gave you nice contrast at short circuit, but everywhere. And there's no deviation from that to give rise to oscillations in the CTF. So that says it as to why this is a better way to produce phase contrast. In Okazaki, Kuniaki Nagayama and Radiston Daniel have been working on this idea for more than 10 years. And they actually have a successful device. And as Barbara told you, you can buy it from JOL now. It's commercially available microscope that has a quarter wave plate for electrons. The quarter wave plate is for a 300 kV electron should be roughly 27 nanometers of evaporated carbon. That consists of a core carbon film that's 17 nanometers thick that has a hole in it. And these hole sizes vary from 0.3 micrometer up to 1 micrometer. And then that core is uniformly wrapped by evaporating more carbon onto it afterward over all the surfaces. And this idea is not so new. It was proposed in 1947 by Birch, and it was taken up by a number of groups. I don't know the whole history. There was a Tone, whose name you know very well, spent a number of years trying to make this thing work, and very little published about it. Some at meetings, a lot of word of mouth, and I formed the prejudiced opinion. It's a bad idea. It doesn't work. And the real reason is because too many of the electrons that have to go through the phase plate and get a phase shift due to the sort of inner or constant component of the Coulomb potential. Too many of them are scattered by the AC components of the Coulomb potential of the carbon film. You lose too many electrons. Well, I didn't change that opinion until I started to see real, genuine, beautiful results coming out of the laboratory a couple of years ago. There's a published paper on ROEL, for example, this year, showing for data collected with a CCD camera at 300 kV and not terribly high magnification, you get identical 3D reconstructions with the phase plate and without the phase plate at about 12 angstrom resolution. And I personally looked at the situation a little bit more, and from estimates of how many electrons would be lost due to scattering, it actually didn't look so bad. And I had the wonderful honor of being invited by Nagayama to spend an extended period, which I did from March to the middle of June. And one of the things that was on my agenda was to measure accurately what is the loss. And we measured that there was a transmission of about 80%. So you'd say 20% of the signal is lost. Wrong. We have weak phase objects. The contrast is not proportional to the intensity of the scattered wave. It's proportional to the amplitude of that wave, or to the square root. So there should only be something like a 10 or 11% loss. When we measured the actual contrast of images with and without the phase plate, with the image defocus to give you a maximum in the CTF and the tone rings, the attenuation is 0.86 rather than 0.89, almost close enough for government.
So it's actually quite a lot difference in.
Well, 14%. Is that a lot? I don't know.
Oh, attenuation is above, actually.
That's not worded correctly. The attenuation corresponds to getting a signal of 86% of what a perfect signal would be. Yeah, there's very little attenuation. So attenuation is not the reason why other labs failed. The main reason why other labs failed, I think, twofold. One is they were not controlling the amount of contamination and charging of their phase plate. In Okazaki, they do it by heating their aperture to 150 degrees centigrade. Secondly, I bet those folks were not drilling small enough holes. I'm not sure they even had the technology in tone state to make sufficiently small holes for the unscattered beam. In Okazaki, they use a focused IMD to drill a very small hole for the unscattered beam. So here's an example of GROEL at about 1 micrometer defocus and with the phase plate. And there's the reference to the published work that I mentioned previously, comparable resolution, comparable reconstruction set at 12 angstrom resolution. So, yep.
If I look at this, the left side, the original without phase plate, you don't find the particles. On
Oh,
the
you
right
can find them.
Yeah, barely. Okay, on the right side, they jump into your eyes, but the risk of losing high resolution. Couldn't you have a much thinner phase plate?
Yeah, I think that's the right way to do it, because then the white halos become much less noticeable as well. Yeah, I agree. So these objects are not actually, strictly speaking, weak phase objects. They're already fairly small, GROEL particles. You'll see it even worse when I show you TMD on the next click. With carbon film, it's difficult to make it thinner because it has to be self-supported over the entire aperture. And it has to be even thinner to begin with when you drill a hole, because it's very important to do the wrapping step. I haven't explained why. I can, but it is important. So one of the advantages of electrostatic devices, you can tune what the phase shift is, and that's the direction that my lab is pursuing. So you have an adjustable phase shift, and you can optimize it for whatever particle you're looking at.
That's why there's still the question. In the vacuum, there's no heat radiation, but this aperture is very close to the specimen.
Yeah, yeah.
The sweet
So the microscope that JOL will sell you, I don't know all the details, but I do know the details of the one that's working in Okazaki right now. But they also bought one of the ones that's being sold now that you could buy. But the one in Okazaki is a 3100, I think, and has a modified objective lens, so the focal length is 5 millimeters, and so the pole piece isn't as long, and now the plane where the focal length of the objective lens is located is still accessible. You can put your aperture there. The original aperture still goes in and acts as a heat shield. So no problem with cryo samples. No problem with stage stability. It's a really elegant modification. All right. There's tobacco mosaic virus. Again, a little over 1 micrometer defocus, and here it is in focus with phase plate. And the reason I wanted to use TMV is because you can do a line trace and integrate the line trace along the length to beat down the noise. So for conventional defocus phase contrast of 1 micrometer, the contrast is about 2%. And for the in-focus phase plate, from the baseline of the ice, there's these ripples through the halos. You see a black ripple that follows. But the contrast under the particle versus the adjacent ice is 10%. So 5 times higher contrast. That means, in terms of your ability to spot this guy, the step from outside to inside, 5 times bigger, means the signal to noise is 25 times bigger. And I think this will make big difference for aligning particles and for assigning Euler angles, but that's not been demonstrated.
Big effects on the positive or on the kind of make it much easier?
I'm sorry?
It means with this white cloud will make the particle alignment much easier.
The white halo, I think, will be neither beneficial nor harmful for the alignment. But the greater contrast, the greater signal at low spatial frequencies will, I think, but it needs to be shown. Okay. But the one that completely astonished me is, as part of a biological project that my little subgroup does single particle reconstructions for a large DOE-funded Genomes to Life program at LBL, the biochemist named Dong sent me a sample called dissimilatory sulfite reductase, so DSR. It's a dimer of enzymatic units that have alpha beta gamma subunit composition, so it's a dimer of that. The whole dimer has molecular weight 200,000. And in particles, they're tumbling in all different orientations. Some exactly end-on, it's pretty much end-on, slightly tilted, etc. The ones that you really see down the two-fold axis, you have no trouble seeing 100K subunit. You could align 100K particles, taken with the phase plate. I don't know how accurately they would align, so Lotto was collecting more data, but he didn't want to collect more on the 3100. He wanted to wait till he got his jazzy new 200 kV microscope, because among other things, it will have a much better CCD camera. And he doesn't believe in recording data on film. He's willing to be patient to get a better CCD camera than record data on the CCD camera. This project is still in progress with him. So this is the point that I was making, that cryo-EM of protein complex is smaller than 400K. This really certainly be one of the major applications. But it remains to be established the extent to which the Zernicke phase contrast either improves or possibly degrades the accuracy of the alignment. But when you have aligned, say, that larger particles, will you be able to better assign particles to different conformational substates because of the much greater clarity of the low resolution information? All open questions at the moment. Now, some time ago, Dieter did a simple calculation to illustrate why it is so important to include the low spatial frequencies. This is just an image of negatively stained tobacco mosaic virus. You can barely see the 23 angstrom layer line. That's an internal spatial frequency calibration on the simulations that were done. And you can see little black holes of increasing diameter. Those are the spatial frequencies that were not transmitted. Calculate the Fourier transform of this image, multiply it by a mass function, calculate the inverse Fourier transform. And the result tells you the extent to which the image is sensitive to the low spatial frequency content. And for TMV, which has a diameter of something like 200 angstroms, if the cut-on is frequency, where you first transmit information and allow contrast to be produced in the image, if that cut-on is 1 over 400 angstroms, it's pretty similar to this. You see the ripples I was talking about, an enhanced halo at the edge, and so forth. And that all gets worse the more you push that cut-on to higher and higher resolution. Already at 1 over 300 angstroms, you have much less contrast than you should have, and by 1 over 200, there's it's looking like a normal cryo-EM sample, and 1 over 100, only after seeing the slide many times do I see the TMV particle there. So the low spatial frequencies are absolutely critical. You must apply a phase shift at low spatial frequencies or you won't see the particle. Now, a little survey slide of some of the alternative technologies that are being actively either pursued or at least talked about to achieve in-focus phase contrast. The thin carbon film, this is the only technology that's been proven to work. And you need the small hole size. I just explained that from Dieter's simulation. And in order, the small hole sizes that you can make in the thin carbon film make it unnecessary to magnify the diffraction pattern very much. So you do want to have, for 300 kV, you want 5 millimeter focal length, so you get twice as big a diffraction pattern. But that's relatively straightforward to do. The challenges, well, let me just go through the best features and then come along and do the challenges. So the microfabricated electrodes, the thing that my group is doing at Berkeley in the NIH grant that we started about a year ago, it will give you a tunable phase shift, and we addressed that in response to Henry's question. It's especially important for strong phase objects to give less than a 90-degree phase shift. That weaker phase shift by the faceplate actually gives a much greater dynamic range or greater linear range of contrast for large particles. And there should be almost no loss. So there is small loss with carbon. There would be even less with the faceplate. Biprism interferometer, often called electron holography, material science people like to call it electron holography, employs technology that has been in use in material science for many, many years, and that would seem to be an advantage. Challenges or the disadvantages. Carbon faceplates, I haven't said so yet, have a very short lifetime, and we don't understand the physics or the materials properties of why that is so. But carbon film is a very reproducible material, and sometimes they will last a few days, sometimes a few weeks. And then you have to replace them. There is this minor loss of signal due to scattering that I've talked about. A challenge or disadvantage of the electrostatic is you have to magnify the diffraction pattern. We would like to have a focal length of 20 millimeters, not 5 millimeters, 5 times larger diffraction pattern, because we can't microfabricate electrodes that will confine the electrical potential, given the phase shift, confine it small enough to get the low spatial frequencies. So we have to blow up the diffraction pattern to be commensurate with the size of our device. And in the experiments we're doing right now, we're trying to find a practical way to avoid the contamination and charging when the electron beam hits such a physical device. The biprism interferometer has a disadvantage that it produces fringes or interference effects in the image that are equivalent to phase contrast over only a very small field of view. You have two sources of unscattered electrons. The unscattered electrons that flow through the specimen and the unscattered electrons that flow through the reference field, and they're both superimposed. So you have twice as much noise. And also the electrons that go through the specimen and the ones that go through the reference field, if the specimen is charging, they experience independent charging effects. And so there has been work in Japan going on for decades to make this work. Hans Lichte in Germany has been trying to make it work. So far, people have decided it's not workable for priority on the samples. And thank Henny for the spreadsheet that I learned about 2 years ago at this workshop, and it's been very helpful to me for calculating CTF functions and envelope functions. Bennett and Nagayama, who I mentioned, who hosted me to do the work that I participated in, and Ming Dong, the biochemistry I talked about, P.G. Han prepared the tobacco mosaic virus for me that I used in those experiments. People working on the static phase project at Berkeley, John Jim is an engineer. Rosanna Candier does, also an engineer, does all the microfabrication. Dieter does a lot of the experiments. And Rosanna Census is our microscopist in charge. He's been participating in the experiments, as has Ken Wong.
Thanks a lot. Questions?
Can you quickly shed light on this white halo? Where does this come from? Is it an effect of the point spread function that's sort of magnified, or where does it come from?
I think of it as something very similar to what's called the Gibbs effect, or the Fourier series termination artifact. And so you see it at lower frequencies than the cut-on. And so when you analyze your data, if you analyze it in Fourier space, the Fourier components that have been Fourier shifted are not affected by it. And so if you use free align, for example, for single particles that's working in Fourier space, you won't even know it's there.
So, in summary, is it correct to say that if you're looking at CS correction of phase plates, if you insert the phase plate, you're recovering, when you're doing the phase shift within the normal framework of the normal CTF that we normally see, but if you include the CS corrector, it allows you to go on to a higher resolution.
Yes.
That's,
Yeah. But except the previous thing you said, if you have the phase plate and you're in focus, there is no CTF correction at all.
Right.
There's no oscillations.
One should mention this is also an advantage that you get rid of delocalization.
Yes,
so if you
yes.
defocus an image, then the information is spread over a relatively large area. And this is concentrated to a very small patch. So this is somehow similar to the effect of the CS corrector in high resolution microscopy.
Yeah.
They also get rid of the delocalization. So it's a CS corrector for biology.
So those of you who haven't already been oversaturated with unfamiliar information, the delocalization effect, explained, someone might say, well, you apply a CTF correction and then it brings it all back. But Ken and I have a paper just it's out now, in ultramicroscopy, showing that only half the information comes back with CTF correction. The other half gets delocalized by twice as much. And it's nothing but so a defocused image is nothing but a Gabor inline hologram. It's very ironic. Gabor proposed holography as a way of overcoming the limitations of spherical aberration in the electron microscope. He used Nature paper. And then it turned out that his holography had a twin image problem. When you restored it, you got a second image defocused twice as much. And that's all that CTF correction does, is the same thing. I'm sure that went.
So this is for electron crystallography. If we have perfect crystals, then we really don't need so much contrast.
No.
But we never have them. We always need the unbending and this lattice distortions. So we want the contrast.
Maybe.
But we cannot afford losing high resolution, and the ceramic carbon messes with the high resolution electrons. We don't want that.
The Zernica messes with the high.
Well, the high resolution electrons are on the outside and they have to go through the carbon film.
You have to go to the carbon.
Yeah, so they get additional inelastic scatterings there, phase shifts, and the carbon is not
Yeah,
smooth.
so 14%. It's very
Okay,
small.
But with
But-
your approach,
But if you're worried about it, yeah, then the electrostatic would not even have.
right, the electrostatic leaves the high resolution electrons in peace.
Yeah.
So that is much more.
But I would not let the perturbations of the carbon film stop anybody from jumping in and buying a JOL microscope that's designed to have a carbon faceplate.
Yeah, I find the fact that Rasmus Schröder came up with a way to deconvolute the asymmetric Hilbert plate effect on the image, I find that very interesting. I've been thinking about how we can in any way disturb only a part of the diffracted electrons. The other half alone. Without any material.
So Nagayama, introduced the idea first, and Rasmus followed up on it to use a carbon film on a half plane. But then the carbon film should be twice the thickness, and the loss of one sideband becomes severe. You no longer actually have the mathematical situation you wanted to have. You lose Friedel symmetry in the amplitudes, and I wouldn't go there at all. But neither will Nagayama. So he's now busy developing instead a bar magnet that's less than half a micrometer diameter. And that, by a physical effect called the Aharonov-Bohm effect, if the magnetic field intensity is correct in that bar magnet, then it causes a high phase shift on one half plane compared to the other. And it will be lossless. And will satisfy the math if you want to use it. So I didn't have that in my.
A wire in one big loop?
It doesn't have to be in a loop, just a straight long one that's much longer than the
Yeah, right, yeah.
What about the lifetimes of the current phase plates and
Yeah.
salt?
Yeah, they seem to vary from a couple of days to a couple of weeks. Most of them a couple of weeks, but sometimes it's disappointing they're not so good after a couple of weeks.
Okay, thank you, Bob.
Yep.
So next speaker is from Downing.
I sort of tuned my talk to the context of electron crystallography, which I presume is the main interest of everybody here. If I need the microphone.
So Ken Downing from the RVL in Berkeley, I think is the first person who really reached very high resolution with 2D crystalline sample from microtubular zinc sheet. Microtubes are round. If you add zinc, this lab developed a method to make super well-ordered 2D crystals. And I brought you, I think, as the first person to what was it, 2 point something angstrom. So originally it has a started field, but you
3.7, but that
you have a very high resolution first.
that came after reduction
After that, okay.
and light harvesting complex. Some people might say even after some aquaporin. I would say.